Okay, so hi everybody. Today's video is on nuclear physics. That is trying to give you a sense of how we know what we know about how the nucleus of an atom works. Now, as you probably already heard, the nucleus is where most of the stuff in an atom is located. Last time we talked mostly about the distribution of electrons around the nucleus. But today we want to focus on the nucleus itself because it is one of those fun places where we get interactions between relativity and quantum mechanics. This time we'll focus mostly on the relativity part. Next time we'll talk a little bit more about the quantum nature of these things. So a nucleus contains two fundamental different types of particles. You have the neutral neutrons and you have the positively charged protons. Now, the protons are particularly interesting because the protons are positively charged, which means that their electrostatic forces are repelling each other. It's surprising that all of the positive charge in a nucleus is basically concentrated in its center, given positive charges want to get away from each other. So there needs to be some other force holding the nucleus together, holding these protons and neutrons together in such a small region of the atom. And there is such a force. It is called, because physicists can be weird when naming things, the strong force. It is a strong force as an actual descriptive name. It is stronger than the electric and magnetic forces that are trying to blow the nucleus apart. So there is some other force besides gravity, besides electromagnetism, that is operating in this region, and it makes a nucleus something that can hold together. Now, the thing is, there's an entire field dedicated to trying to understand this force and understand how it works. And that's kind of tricky because we're talking about something that's happening deep inside atoms. It's not something we could explore just with things I could demo in a room. You know, I can demo electric charge, I can demo magnetic fields, I can even demo gravity. This force turns out to be very hard to demonstrate. There's no way to see it, especially since it seems to only activate in regions of very, very deep inside an atom, on spatial scales of order 10 to the minus 15 meters. But we do know a fair amount about this force. And that's what I kind of want to talk about today, is I want to talk about how we know about this force using a couple of different techniques. And to start with, though, we have to get some definitions down. This is all stuff that is kind of common from chemistry, but I want to be clear about it because it's going to be important going forward. And this is terms like isotope, element, nucleus, and atom. Of course, we've already talked about what atoms and nuclei are. Atoms are basically a nucleus, where all the positive and negative charges are, surrounded by a cloud of electrons. So the nucleus is just the part of the atom that has the positive and negative, the protons and the neutrons. And given the huge difference in scale, I like to show these with cartoons. So I'm going to show nuclei with little red dots to indicate protons, little black dots to indicate neutrons, and laid out in a somewhat regular thing so you can see how many there are, surrounded by a blue cloud of electrons. And these are not to scale, they're just diagrams to help you see what's going on. Now, the properties of a proton or of a nucleus, are dependent on how many protons or neutrons they have. The number of protons is what is critical for determining the chemistry of an atom, because the number of protons sets how many positive charges are in there. So this sets the total positive charge, and that positive charge is what holds the electrons in place and also determines their configurations. So And since the electrons are what interact with other atoms because they're just more dispersed, the chemistry of an atom is determined fundamentally by the number of protons in its nucleus. Now, and atoms with different number of protons in their nucleus have different chemical properties and are thus identified as different elements. A classic example is something with 6 protons in its nucleus is carbon. It has the chemical properties of carbon. Any atom with 6 protons in its nucleus will have those chemical properties. You know, it's an important an important element for biology, etc. If we have something with 7 protons in it, that has a different configuration of electrons around it. This has different chemistry. This is not carbon, this is nitrogen. This is a different element. The chemistry of nitrogen is very different from the chemistry of carbon. So, and this is everything you find in a periodic table. Now, things with the same number of protons can have different number of neutrons. Neutrons don't affect the charge, so they don't affect the chemistry much, but they do affect its mass and also some other properties about it, which we will get into. So if you have an atom, you can have an atom with 6 protons and 6 neutrons, or an atom with 6 protons and 8 neutrons. These are both carbon, but they're different types. And they're conventionally designated by a number, which is just the total number of protons and neutrons. So this with 6 protons and 6 neutrons is carbon 12, because 6 protons and 6 neutrons. This, which has 6 protons and 8 neutrons, is called carbon 14. And the book talks a lot about how you designate this with proper symbology. I'm not going to get into that. These things are called different isotopes of the same element. So these are the kind of things we're going to be looking at and trying to understand. We have different types of atoms, and a basic question we have is, why are these the way they are? How are they held together? Well, to see that, it's important to look at their masses. And when we're looking at the masses of individual atoms, units like kilograms don't make any sense, because the mass of an atom is a very tiny fraction of a kilogram. Typically, when people talk about the mass of an atom, they measure it in terms of what are called atomic mass units, which are designated either AMU or often U. So 1 AMU, for reference, is about 1.66 times 10 to the minus 27 kilograms. Now, that's a small number. Now, it turns out, using this conversion, an isolated proton is 1.00728 AMU. And an isolated neutron is 1.00867 AMU. An electron is a good deal smaller than that. So you put an electron with a proton, you get something with a mass about 1.00784 AMU. Now, you can see the advantage of this unit in that protons and neutrons are both about an AMU. But you might also notice neither one is just 1 AMU. And you might be wondering why that is. And there's a very good reason it's why it is, but at the moment you might just say, oh, is this one of those weird things where units are defined in a way that was once sensible but is not, now not. But this is, you know, a measure of mass that's fairly useful, where protons and neutrons are about 1. And so a hydrogen atom, which is just a proton plus an electron, is also about 1. And the nice thing, and part of the reason we think we understand at a gross level what's going on inside atoms, is that the mass of every atom is pretty much a whole number of AMUs. For example, helium-4 has a mass of about 4 AMUs. Carbon-12, which is a mass of about 12 AMUs, which makes sense. Helium is supposed to contain 2 protons, 2 neutrons, and 2 electrons. Carbon-12 has 6 protons, 6 neutrons, 6 electrons. That all makes sense. And you look at basically a table of atomic masses, you'll see everything's pretty close to a whole number, but not exactly. And this is where things get potentially interesting. If you just said like, okay, this is 1, this is 4, this is 12, you'd go, okay, that gives me confidence that these things are what you say they are. And by the way, you can also figure out which are protons and which are neutrons just by figuring out the charge on the nucleus, which, we know how to do that. The reason all of these decimal points after the whole number are important is they reveal some surprises. Again, the hydrogen atom has a mass of about 1.00783 or 4, which is just the mass of a proton plus an electron, more or less. And so that's fine. It's just, why did you define AMU that way? But you just go, okay, that's fine. The mass of a helium-4 atom is not just 4, it's 4.003. Notice that. This is 2 protons, 2 neutrons, and 2 electrons. So you might say, well, okay, protons and neutrons are close to the same mass. It should be about 4 times this number. And you go, well, it is 4, that's good. But if you multiply 0.0078 by 4, you don't get this. Notice the remainder is less than the remainder of this. If you actually add up the parts, you get 4.033. This thing is less massive than 2 protons, 2 neutrons, and 2 electrons in isolation. That is not a measurement error. You can measure mass really well. This is real. Carbon-12 is even more extreme. Carbon-12 actually turns out to be exactly 12 AMU in mass. This is how it was actually defined. This thing is, again, less massive than its component parts. If you take 6 isolated protons, add 6 isolated neutrons, and 6 isolated electrons, you get more like 12.1 AMU, but the actual mass is less. This is weird. You have things, atoms, that have less mass than the sum of their parts. From our commonplace experience, this doesn't make sense. This implies we made a measurement error. Something is going on here. And it's a real effect. And that mass difference is critical for understanding how these atoms are held together. And the key point is to come back to that equation from relativity, E equals mc squared, which says there's an energy associated with every mass. So let's think about that in the context of, say, this atom of helium, which has 2 protons, 2 neutrons, and 2 electrons in orbit about it. Again, its mass is 4.003. If I wanted to take this apart and pull it into all of its pieces, 2 protons, 2 neutrons, and an electron and a pair of electrons, that disassembled thing is 4.033 atomic mass units. This is more mass than this. So if I wanted to take a helium atom apart, the system would need to increase in mass somehow. And again, this is nothing that we have day-to-day experience with. I cannot take a couple of, lead bricks, pull them apart, and have something that weighs less than 2 lead bricks. Something weird is going on here. What's important to understand is at this level, what's happening is mass is not something that's unchangeable. Mass can change at this subatomic level. But other rules still apply. Specifically, this relationship between energy and mass. Remember, what we saw from the relativity thing was that Einstein's analysis of energy and momentum showed that even an object just sitting still with mass had energy associated with it. So that is a profound statement. It means that if mass changes, energy changes. So if we go from this thing to this collection of particles, we have increased the mass, which means we've increased the energy of the system. Remember, fundamental physics is energy is conserved. That's how energy is defined. It cannot change. That means to do this, to take an atom apart into its component particles, requires increasing its energy. You need to add energy to this system to pull it apart. That's a critical statement. It means that you have to take energy from outside the atom and put it into it to break it apart. This is relevant because it means if you pull these protons out, as they might like to do because they're electrically repelled from each other, that actually that doesn't release energy, it requires energy for this particular configuration. So it can't fall apart on its own. The atom, as it is here, cannot transition to this state without outside help. And it actually requires quite a bit of outside help because you can calculate how much energy you need to do to break this atom up. You just use E equals mc squared. Well, what's the extra energy you needed to put in? It's just the difference in the masses, which is 4.033 minus 4.0026. Convert that to kilograms by multiplying it by 1.66 times 10 to the minus 27 kilograms per AMU, and then multiply that by the speed of light squared, and you get 4.5 times 10 to the minus 12 joules, which is a small number of joules, but it's in an atom, which is a very small thing. To understand kind of what's the scale of this energy, it's useful to recast joules into the other unit of energy we talked about back in section 1, I think, electron volts. It turns out it's 28 million electron volts. Now remember, what is an electron volt? Why am I using it here? If you have a potential difference of 28 million volts and have an electron run across that electric potential, it will get a kinetic energy of 28 million electron volts. Now, the way you would break this up in practice is you would send a charged particle screaming into it, collide, and have it break up. In order to do that, you would need that particle to have a kinetic energy of 28 million electron volts. You could do that with an electron. There are plenty of them around, and you can accelerate them. To break up a helium nucleus into all of its component parts would require accelerating that electron that you're going to throw into it with 28 million volts. So you would need a electrostatic potential of 28 million volts to get something going fast enough so that when it hit this nucleus, it broke it into its pieces. That should at least give you some sense of how tightly bound this is. It takes a lot of energy to pull it apart. So this is saying this just can't happen. You can't have all 4 protons and neutrons get pulled apart. They just won't do it on their own because there aren't electrons or other particles running around at those speeds very often. You could make it happen, but it's not going to happen naturally in the wild very often. Now, that's one particular change. You could imagine other changes. Like, instead of trying to pull all 4 apart, you could imagine pulling out a neutron and just having a proton and two protons and 1 neutron. You could imagine pulling out a proton, or you could split it in half, having protons and neutrons with their own electron clouds around. These are different forms of helium and hydrogen. This is helium-3 because it's got 2 protons and 1 neutron. This is hydrogen-1, normal hydrogen. This is hydrogen-3, which has a proton and 2 neutrons. It's also called tritium. These are 1 proton and 1 neutron. They're called hydrogen-2 or deuterium because everyone has to give everything special names. But what you can do is say, well, what's the mass of this thing? Works out to be 4.024. The mass of this thing also works out to be about 4.024. The mass of this thing turns out to be about 4.028. All of them are more than this. There is no way to break up this nucleus, or atom, but more importantly, the nucleus, that doesn't result in an increase in mass. So all of these transitions, even if you just tried to yank out the neutron, which you might think, oh, that might not be too bad, or just yank out 1 proton, each of these requires adding energy. And what this is telling us that this atom basically can't change to anything else, at least as long as protons and neutrons can't disappear, which they don't seem to be able to do. So an atom like this is completely stable. It won't fall apart on itself. And these mass differences, like what happens if you yank out a neutron or yank out a proton, give you a measure of how tightly whatever this strong force is holding together these protons and neutrons. You can note that pulling out a proton and pulling out a neutron results in systems with slightly different masses. That tells you that protons and neutrons are held in slightly different ways. And you can use that to work out how this force actually works. Now, this is true. Now, this particular pattern where basically pulling the atom apart any possible way just results in a mass increase and thus would require energy, that's the case for most atoms we experience in our lives. I mean, it's true for most carbon, it's true for most hydrogen, it's true for most of the materials we experience. It's not true for all of them. This is where we get into the other topic of radioactivity. There are certain atoms, isotopes of certain elements, that spontaneously emit high energy particles. Now, there are 3 basic types of particles. Now, this is the stuff you've heard about, like uranium and various other fun, uranium, plutonium, those sorts of things. Or radium and radon as well. And the thing is, these types of atoms emit a variety of different types of radiation. And I want to try and be clear about one thing here. We're now talking about something slightly different than the electromagnetic radiation I talked about before. Electromagnetic radiation, which can be anything from radio waves to gamma rays, is a disturbance in the electromagnetic field and is fundamentally neutral. These things coming out of these specific types of atoms don't have to have that property. In fact, people figured out what these were by letting these particles go through magnetic fields and seeing that they deflect. You could use the right-hand rule and figure out that positive charges are deflected one way, negative charges will be deflected the other, neutral particles, because they don't have a charge, won't be deflected. And in general, there's three types of this radiation from nuclei or from individual atoms. There are what are called alpha, beta, and gamma rays. And these names were developed a long time before we fully understood what the structure of the atom is. So each of these things is also another thing. But they have very different properties. Alpha particles are positive things, and they have the property that you can stop them from going anywhere with just a sheet of paper. Beta particles are typically negative, and they can go through sheets of paper, but they can't go through more than a thin sheet of metal. Gamma rays, which are uncharged and actually are a type of electromagnetic radiation, are neutral and can penetrate through a few inches of lead or lots of concrete. Gamma radiation is highly penetrating, alpha radiation is not. For those of you health physicists, they're people interested in health physics. This doesn't mean one is more or less toxic than the other. Gamma rays mean it's harder to block if there's a source outside of you. So if you have something sitting next to you that's emitting gamma rays, it can get to you relatively easily. But if you accidentally ingest some of this material, alpha particles are not great because they don't escape you. They do something instead of just going straight through you to the outside world, they can bounce around inside of you and do damage because these are all pretty energetic particles. And what we think they are the representation of nuclei partially breaking. So our current understanding, based on lots of experiments that I'm not going to go into, is these are three different types of nuclear transformation, specific to the nucleus, not to the atom. Alpha particles are the same thing as the nucleus of a helium atom, a pair of protons and a pair of neutrons. This sort of thing happening implies the nucleus actually broke. That is, a chunk of the nucleus came off in the form of particularly 2 protons and 2 neutrons. That means whatever's left has to have 2 less protons and 2 less neutrons. Fine. Beta particles turn out to be mostly electrons, or technically an anti-electron or a positron. When these come out of the nucleus, because they're negatively charged, something had to change in terms of the charge state of the nucleus. Since an electron's negatively charged, the nucleus has to be more positively charged now. So what happens is one of the neutrons, which is a neutral body, turns into a positively charged thing and shoots out an electron. It also shoots out another type of particle called a neutrino, which is a truly neutral particle that is interesting in and of itself, but not the subject of today's video. Gamma rays are an electromagnetic wave again. These are very high energy electromagnetic waves. They do not affect either the number of protons or the number of neutrons. And we'll get to them last. And so what I want to do now is talk a little bit about each of these different types of transformations, or what are called nuclear decays, and how they can possibly happen. So let's start with alpha particles, or alpha radiation. Now, this is something that typically happens with fairly large nuclei, like like uranium or plutonium. So, for example, uranium-238, which I'm not going to draw all of them, so I use this figure from the textbook, has 92 protons, 146 neutrons, and a mass of 238.0508 AMU. This thing does undergo alpha decay, so it produces a helium nucleus, and what's left over is thorium-234, which has 90 protons, 144 neutrons, and has a mass of 234.0436 AMU. This thing is, of course, a helium nucleus with just 2 protons, 2 neutrons, and a mass of 4.0026 AMU. So these are all measurable things. But what's interesting in this particular case is that the sum of these two masses works out to be 238.046 AMU. It is less than the mass of the uranium nucleus. That means this transformation, and particularly this transformation, reduces the mass. It's going to, so this reduces mass. It doesn't require energy to happen. It releases energy when it does happen. There's no need for energy to go into the nucleus to make this happen. So it can just happen on its own. And indeed, it does. Uranium-238 does spontaneously do this. We can measure it. And it produces an alpha particle. But it doesn't just produce a helium nucleus. It makes a helium nucleus that's going very quickly. Why is that? Well, this mass decrease has to go somewhere. Or sorry, when this mass decreases, the energy, the mass energy, the E equals mc squared energy, goes down, but energy is always conserved. So that mass energy has to go into another form of energy, specifically kinetic energy. It goes into the motion of these two things, and since this is the lighter of them, it tends to get a lot of it. And you can actually calculate how fast this is going to come flying out. You've got the change in energy due to the change in mass. That's just the change in mass, 0.00046 AMU, which isn't very much, times c squared, which is a big number. That decrease in mass energy has to equal the increase in kinetic energy, which, like I said, mostly goes into the lighter nucleus. This is mechanics if you want to do this properly. So this has to equal 1/2 the mass of this alpha particle, which is about 4, and how fast it's going, v. So we know m alpha, we know delta m, we know c squared, we can solve for v. Turns out v is about 1% the speed of light. This thing comes flying out. It releases a lot of energy. And people measure these sorts of things, and it all works out. So this apparently can happen for certain types of atoms, certain isotopes of particular elements. And it's just literally an atom falling apart. Now, it turns out helium nuclei are the easiest things to throw out because this turns out to be one of the more stable nuclei, which we may get into on the next video. So that's sensible, partially. More exotic is beta radiation, because this doesn't involve the nucleus falling apart per se, but instead involves a change in one of the protons or neutrons. Again, there's actually two different types of this, one called beta minus decay and one called beta plus decay. One of the more famous nuclei that undergoes beta minus decay is carbon-14, which is again a form of carbon. It has 6 protons and 8 neutrons. This undergoes beta decay where it emits an electron and a neutrino and turns into nitrogen, which has 7 protons and 7 neutrons. Now, if you go look up the numbers, you find that the mass of this thing is 14.003242, whereas the mass of this thing, plus the electron and keeping track of all of that, is 14.003074 AMU. So this transformation is again allowed by E equals mc squared. It reduces in mass, which means it releases energy, which means it can just happen. You don't need to add anything to it. There are other transformations that are observed that are similar to this. They're called beta plus decay. In this case, you have something like, say, sodium-22, which has 11 protons and 11 neutrons, transform into neon-22, which has 10 protons and 12 neutrons. So in this case, a proton, this one, turned into a neutron. Now, since we had one positive charge go to a neutral, the thing that comes flying out has to be positively charged. And it is. But what it turns out to be is something the same mass as an electron. And turns out when a positron and electron smack into each other, they just release light. This is something that is sometimes called an anti-electron. So this is an exotic particle that often doesn't last very long until it finds another electron and blows up and produces light. So sometimes this can almost look like it's doing gamma decay, but it's technically not. But again, the transition involves something with a mass of 21.9944 going to a mass of 21.99139. Again, the mass goes down, so energy is released. This can happen. Protons can become neutrons, neutrons can become protons. Okay, so apparently protons and neutrons can transform into each other. That's apparently allowed. We've never seen a case where a proton has spontaneously disappeared from existence. That would violate charge conservation. If we could ever see a positive charge just disappear, that would be really cool. Nobody's seen it. We also don't see neutrons just appear or disappear. They can convert into protons, but they don't just come into being, at least not in normal situations. One important thing, though, is you don't experience you don't experience neutrons just in your day-to-day life. We have hydrogen atoms around, which are more or less just a proton and an electron, but we don't have isolated neutrons. That's because of the same process. An isolated neutron is 1.0087 AMU. An isolated proton plus an isolated electron, that's a hydrogen atom, is 1.0078 AMU. A proton and an electron together are less massive than a neutron. So any isolated neutron will and does just transform into a proton and an electron. So That's why we don't see isolated neutrons very often. You have to make them by crashing other things together. But a neutron just falls apart into a proton and an electron. That's okay. It's something that's neutral that pulls apart into a proton, into something that's positive and something that's negative. Okay. One thing I want to deal with is that gives an impression like, wait a minute, a hydrogen atom is just a proton and an electron, just in orbit around each other, so it looks neutral. Is a neutron just kind of the same thing? Is it really just a proton and an electron, like really tightly bound? And it's reasonable to consider that, but it don't work. A really basic reason is that a proton and an electron are oppositely charged. They're attracted to each other. So if you could somehow smush the electron in a hydrogen atom even closer to the nucleus, that should release energy and reduce the mass. In fact, you do that, you get the electron into the proton to make a neutron, the mass goes up. That says something else is going on here. The neutron is actually a different particle than some sort of weird proton-electron hybrid. And this is the start of a field called particle physics, which seeks to understand like what these fundamental units of atoms actually are and leads to the discovery of things like quarks and many other exotic particles. But that's a little bit of an aside on this particular lecture where we're focusing on what these things are. So what's interesting is the types, very specific type of atoms undergo very specific types of decay. You can find various versions of this online, but this is a plot I like, which shows for different elements and isotopes, the number of protons on the x-axis, the number of neutrons on the vertical axis, and the color code indicates different types of atoms and whether they're stable. The black ones are ones that never transform unless somebody does something to them, or unstable. And whether they undergo alpha decay, that is, they split apart, which are the yellow ones, which you'll notice are mostly up here at the high end with lots of neutrons and lots of protons, or whether they undergo different types of beta decay, which are these ones in orange and blue, which are more common with lower numbers of neutrons and protons. But you notice there's lots of structure in here. Like there's kind of alpha particles that there are some alpha decayers that are right here. There are some particular number of protons, certain elements that are never stable. You actually can look here. There are certain values of the number of neutrons that are never stable, like these guys, or anything up here. And another one here and here. This is telling us important information for how these atoms are held together, the nature of this specific force. We can now say, oh, if you add an extra proton or add an extra neutron, does it make it stable or does it make it want to fall apart? And along with that, and what's actually a lot more useful, is the fact we have masses for all these things. And again, what those masses are telling us is how tightly bound together all of these different nuclei are. It's this that formed the basis of a lot of our understanding of how this strong nuclear force is holding the atom together. Now, but there's one other type of radiation I should mention before I end for this, and that is gamma radiation. Gamma radiation doesn't change the number of neutrons or protons, but the energy of these photons is really high. It's comparable to the kinetic energy of certain types of alpha and beta particles. And this is way higher energy than anything you get from, say, electrons changing states. But it's the same fundamental process. These gamma rays are electromagnetic radiation. but they're not emerging from the electrons, they're emerging from the protons in the nucleus, mostly. What's happening here is a nucleus is doing something and releasing energy. That is like how when an electron goes between quantum states, it can release energy. It can release electromagnetic waves or light with a very particular energy. This is the case here. These gamma rays have very specific energies. What's happening is that the nucleus has the same number of protons and neutrons. It's the same isotope of an element, but something about the configuration of the protons and neutrons is changing and allowing it to release energy. Now, the way this usually happens is that this thing is the product of one of the decay events, like either an alpha or a beta decay. That leaves a nucleus that's not quite in its ground state, not quite in its lowest energy state. So the protons and neutrons then reconfigure themselves, and that releases enough energy to produce a gamma ray. And again, what this is telling us, what the energy of this is telling us, is what's the energy of these different states of the nucleus. Just by how looking at the light from different atoms could tell us what are the configurations of electrons around a nucleus, the energies of these photons, these gamma rays, which come from nuclei. Studying those tells us the different states that can exist within a nucleus. And getting them into these states is pretty hard, but you can do that. So what I'm hoping I've shown you in this particular video is how we're able to understand what's going on inside a nucleus. By looking at their masses and looking at these different decay chains, we can learn a lot about the force that's holding these things together. In the next video, what I want to focus on are some practical aspects of this, as in, how you could use this to generate power, also how these transformations occur. It turns out an unstable nucleus doesn't just transform immediately. It takes some time. That's one of the ways we can use nuclei as a technique for dating, and also means we can have it sitting around and understand how much radiation it's going to produce. So that's next time. Thank you all for your attention, and see you then.